In this video, we're going to introduce the concept of magnetic flux. Magnetic flux is a key component of another physics theory called Faraday's law. So Faraday's law tells us about a relationship between changing magnetic fields and electric fields. But to understand Faraday's law, we first need to understand magnetic flux. So in this video, we're only going to cover magnetic flux. And in a future video, we will talk about its application to Faraday's law. Okay, so the definition of magnetic flux, it is the integral of the magnetic field dotted with an area vector. In the general case where the magnetic field is allowed to change throughout the area, we have this equation, integral of B dot dA. If the magnetic field is constant, we have this simpler equation, which is just the magnetic field dotted with the area. Okay, so what does this mean? What area are we talking about? What magnetic field are we talking about? In order to understand what magnetic flux is, let's begin by trying to understand the area vector, A. So in order to have an area vector, I need some kind of a loop that encloses some area. So it would be the surface area. A vector is referencing the surface area enclosed by this loop. So the A vector has area equal to the area inside of the loop, and it has a direction which is perpendicular to that area. So for example, if I have a loop, so this picture has a loop lying flat in the plane like this. If I have a loop like this, the area vector would have magnitude of pi r squared, the area of a circle, and it would point in the y-hat direction, because that is the direction that is perpendicular to this surface, right? So if I have some surface area, the area vector is always going to be perpendicular to that surface. However I orient the loop, I need the area vector to point straight out of that surface area. So here I'm just kind of moving the loop around and showing the direction of the area vector as I move the loop. It always points straight out of the loop. Now, an obvious question would be, well, yeah, but down is also perpendicular to this surface. And that's true. And there's no particular reason to choose the area vector to point up or down. And in the end, it won't really matter which direction we choose. So we can choose the area vector to be up or down. The important point is that it is perpendicular to the surface of that loop. So either way you want to pick it is fine. The magnitude of the area vector must be equal to the area enclosed by the loop, but you have two choices for the direction, in this case, plus y hat or minus y hat. Okay, another A vector here. So in this case, we have a sheet of paper. So this would be a loop surrounding a sheet of paper, like say a book. So here I have a book. We can imagine that there is a loop surrounding this book, and therefore the area enclosed by the loop is just the surface area of the cover of this book. The area vector will point perpendicular to that surface area. So in this case, if the book has a width of z and a height of y, the area vector, if I assign the book to be this way, will have an area of z times y, that is the surface area of our book, in the positive y-hat direction because I have oriented the book in this way. And here we are, of course, using our standard coordinates. Positive x is to the right, positive y is upward, and positive z is out of the page, which makes to the right our positive x direction, right? And again, I could choose my area vector to be in the negative x direction, and it wouldn't end up affecting my physics, whichever way I decide to choose. But those are my only two options. Either it's to the right or it's to the left. Now that we've described the area vector for these two situations, let's look at what B dot A is in each of these cases. So let's imagine that I have a magnetic field with some magnitude that I will just generically call B, pointing in the positive y direction throughout the entire board. Okay, so in this case, my magnetic flux B dot A is equal to B y hat, because B points in the positive y hat direction here, dotted with my area vector, pi r squared y hat. Remember, when we take a dot product, we multiply like components, so the x hat times x hat, y hat times y hat. In this case, there's no x hat component, nor is there a z hat component to worry about when we take the dot product. But when we take this dot product, we multiply the y component by the y component and get this value here. So our magnetic flux for this situation is equal to the magnetic field multiplied by the area. Now, notice that if I increase the radius, that is, if I stretch my circle out, my flux increases, or if I increase the strength of my magnetic field, my flux increases. Now let's look at our other loop. So remember, this loop is a square loop or a rectangular loop where the face of the loop here is pointing to the right in the positive x hat direction. So this loop is just like our circular loop, except that it's a square, and its area vector is only in the x hat direction. Well, in this case, when we take the dot product of the magnetic field dotted with the area, well, the dot product of a vector that points only in the y direction with a vector that points only in the x direction is 0, because we multiply like components. So the y hat component gets multiplied by the y hat component, the x hat component gets multiplied by the x hat component, but the x hat component of the magnetic field is 0, and the y hat component of the area vector is 0. So there are no components that are both non-zero in both of these vectors. And so all of our terms are 0. That is, that the total magnetic flux through this loop is in fact 0. One shorthand way of thinking about this is that in order to have a magnetic flux, we need magnetic field vectors to move through the area. That is to say, if I have a loop like this, these magnetic field vectors would push through my loop, right? But if I have a loop, and of course this one's square, but I'll still use my circular loop. If my loop points this way, my magnetic field vectors move past my loop, but do not go through the loop. So if you have magnetic field vectors that move past the loop but not through it, you will end up with a 0 magnetic flux, which is the same as saying that the dot product of these two vectors is 0. This is just a nice handy visualization for when are you going to get 0 flux? If the magnetic field vectors move past the loop completely perpendicular to the area vector. Now let's do another quick example of the magnetic flux. So instead of having a magnetic field in the positive y direction, we now have a magnetic field in the positive x direction. Okay, well, we can still do B dot A vector. Our A vector in each case has not changed. In this case, though, now our magnetic field is not passing through this loop, it is passing by the loop, right? Our loop is in this horizontal plane, and the magnetic field vectors are moving past it, not through it. So that means that the magnetic flux here is 0, and we can see that from the dot product as well. Bx hat dot pi r squared y hat leads to 0 because the magnetic field is perpendicular to my area vector. Likewise, now our square loop here, the magnetic field points in the same direction as our area vector, and now we have a b in the x hat direction multiplied by a zy in the x hat direction as well, giving us a flux of bzy, magnetic field multiplied by area. Now, if you're wondering what happens if I take the A vector to be to the left instead of to the right, well, all that happens is we pick up an extra minus sign here, so our area vector would suddenly be zy in the negative x hat direction, which would make our dot product negative here as well. So we would pick up an additional minus sign in our flux here. But the reason that we care about flux in the end is for Faraday's law, and Faraday's law only depends on the change in the flux. So how is the flux changing, not what is the absolute value of that flux. And so in the end, it ends up not mattering which direction I pick here or whether my flux is positive or negative. It only ends up mattering how that flux is changing over time. Now let's see what happens if we put the magnetic field at some angle, say 30 degrees. So here the magnetic field points up and to the right. In this case, we can write our magnetic field vector as some magnitude of the magnetic field multiplied by cosine 30 degrees x hat plus sine 30 degrees y hat. We're just breaking it up into components along the x and y directions like we would normally do. Then we dot this with our A vector here, pi r squared y hat. Well, again, we multiply x hat components by x hat components, but there's no x hat component in our area vector. So the only thing that pops out is the sine 30 degrees multiplied by pi r squared. So we get the magnitude of the magnetic field multiplied by the area multiplied by the sine of 30 degrees. Obviously, the sine of 30 degrees is less than 1. So what's happened is that our magnetic flux has been decreased because now we have tilted our magnetic field at some angle relative to the A vector. Of course, when we tipped our magnetic field at a 90-degree angle to our A vector, that is, we put it in the x direction, we got 0 flux. So your maximum flux will occur when your magnetic field points in the direction of your A vector. Now here I'm only worried about magnitudes. Of course you could get a negative flux here, but since again we don't really care about the minus sign because we're only going to end up taking derivatives of this flux, I guess we could say that the maximum magnitude of flux that you will get for some area and some magnetic field is when that magnetic field is perfectly aligned or anti-aligned with your area vector. Any tilt of the magnetic field will decrease the flux through your loop until your magnetic field is fully perpendicular, in which case your flux will be 0. Okay, so for this loop we get this result for our flux. Let's check out the other loop. So the other loop has an area vector pointing in the x direction. Again, we write our magnetic field as some magnetic field vector magnitude, cosine 30 degrees x hat plus sine 30 degrees y hat. And then we dot it with our area vector zy x hat. This time, the only component that sticks around is the x hat component, and we get the flux, the magnetic flux is equal to the magnetic field multiplied by the area, z times y, multiplied by the cosine of 30 degrees. Again, the cosine of 30 degrees is less than 1, so our flux is less than it was when our magnetic field pointed entirely in the x direction. One more thing that I just want to note is that there is a general form that we can use if we know the angle between the A vector, the area vector, and the magnetic field vector. And that is A dot B equals the magnitude of A multiplied by the magnitude of B multiplied by the cosine of the angle between the two vectors. So clearly this works in this case. Our A vector points to the right, our magnetic field vector makes a 30-degree angle, and we found that our flux is B multiplied by A magnitude multiplied by the cosine of 30 degrees. Now, in the other case, we actually found an equation that says the flux is B multiplied by the area multiplied by the sine of 30 degrees. The caveat here is, or the key here is that our 30-degree angle was not the angle between our magnetic field vector and our area vector. It was the angle between our magnetic field vector and the x-axis. The angle between the area vector and the magnetic field vector is actually 60 degrees. And so we can actually rewrite this equation as b times pi r squared multiplied by the cosine of 60 degrees. And you'll remember from trigonometry, you can also just plug it into your calculator and check, the sine of 30 degrees and the sine of 60 degrees are the same thing. That is to say that in this case here, we can also write b dot a or a dot b, they're the same thing. Flipping the order of the dot product does not change the dot product. Our flux is BA cosine of the angle between the vectors, 60 degrees, which we just needed to take one more step to be able to put it in this form of drawing our picture and realizing that the angle we were given, 30 degrees, is not the angle between the magnetic field and the area vector. This formula will come in handy when we know the angle between two vectors. One more thing that I just want to note is that there is a general form that we can use if we know the angle between the A vector, the area vector, and the magnetic field vector. And that is A dot B equals the magnitude of A multiplied by the magnitude of B multiplied by the cosine of the angle between the two vectors. So clearly this works in this case. Our A vector points to the right, our magnetic field vector makes a 30-degree angle, and we found that our flux is B multiplied by A magnitude multiplied by the cosine of 30 degrees. Now, in the other case, we actually found an equation that says the flux is B multiplied by the area multiplied by the sine of 30 degrees. The caveat here is, or the key here is that our 30-degree angle was not the angle between our magnetic field vector and our area vector. It was the angle between our magnetic field vector and the x-axis. The angle between the area vector and the magnetic field vector is actually 60 degrees. And so we can actually rewrite this equation as b times pi r squared multiplied by the cosine of 60 degrees. And you'll remember from trigonometry, you can also just plug it into your calculator and check, the sine of 30 degrees and the sine of 60 degrees are the same thing. That is to say that in this case here, we can also write b dot a or a dot b, they're the same thing. Flipping the order of the dot product does not change the dot product. Our flux is BA cosine of the angle between the vectors, 60 degrees, which we just needed to take one more step to be able to put it in this form of drawing our picture and realizing that the angle we were given, 30 degrees, is not the angle between the magnetic field and the area vector. This formula will be particularly handy if we know the angle between two vectors, particularly if we know that the angle between the area vector and the magnetic field vector is 90 degrees, right? If the area between those two vectors is 90 degrees, the cosine of 90 degrees is 0, so our flux is 0, right? If the area between our two vectors is 0 degrees, well then the cosine of 0 is just 1. The two vectors point in the same direction, and our flux is simply A multiplied by B, the magnitude of A multiplied by the magnitude of B. So this can be a handy shortcut if we need it to be.